today we will mainly consider the situation where there is some kind of a system running, experiment running, and out of that you are getting a time series information. What does it mean? For example, there is a electronic circuit which is operating maybe periodically, maybe chaotically, some way, and suppose there is a current that is coming, you are sensing the current. Whenever you sense the current, some natural questions crop up. For example, suppose that current passes through a resistor, how much power will be dissipated? Now, for a DC current, this is a trivial question. For a AC current, sinusoid, there also you know how to do it, how to handle it. But what happens if it is a chaotic waveform that passes through a resistor? How much will be the power dissipated? You might also imagine the situation that the current is not just a sinusoidal quantity, but a DC value on top of which there is some kind of a time varying quantity. One would naturally like to find out what is the DC component of that. One would also naturally like to find out what is the AC component of that. AC means here I am not talking about the sinusoidal waveform, but the component that remains after having taken out the DC component. I am talking about that. One would also be interested in finding out the variance, standard deviation. One would also be interested in finding out the spectral characteristics, or how much is the state at a particular time dependent on the history. So, these are the issues that one tries to look for when one encounters a time series. So, by time series I will mean that there is a system running. There is a system running means it could be any dimensional system, it could be 3 dimensional, 4 dimensional, but you are being able to access, observe, measure one of the state variables, and thereby you are getting a waveform. And then you are facing the question, what do I learn from this waveform? So, let us first, by the way, the same kind of problems are encountered in any signal processing application. So, naturally the things that I will be covering, many of these are basically the same as that covered in any signal processing course. So, for those who have done that kind of courses, it might be repetition, but since there is a inhomogeneity in the class, nature of the class, I have to cover all this. Okay, the first question, if say the current that I am talking about passes through a resistor, suppose it is a 1 ohm resistor, how much power will be dissipated? How to find out from that waveform? Now, that is obviously given by the mean square value, square because I square r, it will be dependent on the square term. So, the mean square value will be given as, that would be integral of 0 to t and square of the term x square t dt, that has to be averaged out. Then you have to consider this t going to infinity, right. So, limit so this is the quantity, x t is the quantity that you had. If you calculate this, you essentially get an idea about this is the mean square value. So, it will give an indication of if the current passed through a 1 ohm resistor, how much power will be dissipated. Obviously, this could be just any waveform. You only need to have the time series available to you. You would also be interested in the average value, right. What would the average value indicate? The DC value essentially. So, the average value would be, I will write it as mu x is again limit t tending to infinity 1 by t, but now I will be summing up, I will be integrating over integrating x t dt, right, obviously. So, here we have x square t to get the mean square value, and this is the average value. Or DC value. So, if x t is simply a sinusoid waveform, then what do you get here? 0, right. So, these are reasonably trivial stuff. The rest of the component, which can be viewed as the AC component, would be the variance from the average DC value. So, there is a DC value and on top of it there is some variation. So, that has to be then measured to give you the DC value. These are important, for example, in the context of, say you have a, from electrical engineering point of view, say you have a DC to DC converter, you know that there is a DC value which you want at the output, but there is inevitably a ripple component of it. And the output actually utilizes the DC value, but there is a DC value plus an AC value that is contained in the final output waveform. So, the AC value is actually useless in this case. So, that is why it is necessary to measure, and in case this waveform turns to be periodic, aperiodic, whatever, all the time you will be interested in finding out that additional component. So, that component, the variance component, would be again limit t tending to infinity 1 by t, but what will you integrate in this case? In this case, you will integrate x t minus this quantity, right, and then you will square it, because you want to find the mean square of that value. It is a AC component, you want to get a mean square of that value.
So, in the first and second step, why the limit t tend to 0, t tend to infinity?
No, it is t tend to 0, it is t tend to infinity.
So, what if you integrate from 0 to t, then there will be no small t term left.
Oh, I am sorry.
Yes.
Yeah, of course. So, essentially you are taking a very long, ideally infinite length of data. Obviously, you will not get a infinite length of data, but that is the total length t I am talking about. So, capital T tending to infinity means ideally we will consider an infinite length of data. So, this is what the variance component. So, these are the three things that would be really practically important for various situations, and these would be the same for any waveform as good in case of the chaotic waveforms. But then we will come back to this and try to relate this with many other quantities that we will be interested in. By the way, what is standard deviation? Square root of the variance. Okay. Now, in an earlier class, I had talked about the density function, did I not? There our basic point was, okay, let me recapitulate that a bit. The situation is that at that time we were talking in terms of maps, and in the map, or as the map was iterated, we tried to find out the densities and the density function. but here we are talking about some experimental data. And as we are getting the experimental data, there also a question of the probability density function will arise, in the sense that suppose there is a data set that is coming, I ask what is the probability of finding the state, that particular value that is being measured within a certain band of values. For example, if I am measuring current, I say what is the probability of finding the current at any instant of time between 1 ampere and 1.1 ampere. So, this is a valid question to ask, and in order to obtain that, all we will do is to measure this, to obtain this, and find out of the whole range of time, for how much time did the data set spend in that particular range, 1 to 1.1 amperes. Okay. So, essentially what are we doing? We are saying that suppose we are considering the range x to x plus delta x. Within this, suppose it spends a time t x, and the total time is t. In that case, obviously, what is the probability of finding the state in that range is t by t x by t. Okay. There is no difficulty about it. So, we would say that the probability of finding x, probability of finding x t in the range x okay, is that clear? X t to fall in the range x to x plus delta x, the probability of that is nothing but t x by t for t tending to infinity, for okay, we need to take large value. So, if we take a finite length of data, then we basically get an approximation of this probability. Ideally, you have to take an infinite length of data, then only you can say this. So, we have a measure of the probability t x by t, and that gives you the probability of finding the state in that particular range. Now, the probability density function will be then given where this delta x is squeezed to 0. Okay. So, if delta is squeezed to 0, then what is the probability? That will be that will give the probability density function. So, it is p of x is limit delta x tending to 0. Then we will talk about the probability of x t lying in the range okay, divided by delta x. So, this is the probability. Now, I divide by delta x and allow delta x to 0. So, if this is the waveform, I said that this is the range that I will be talking about. First, we find the time that the waveform spent in this particular range. Where is it at x? How broad is it? Delta x. And then we found the probability and then divided that by delta x and allowed delta x to 0. That as a function of x, that means where I am trying to find it, if I calculate that, that gives me the probability density function. Is that clear? As referred to a data set, a signal. So, here is the idea of the probability density function. Obviously, the probability of finding the state between the range x1 and x2 would be what is the range? What is the probability? It is nothing but x1 to x2 p x okay. Fine. So, once we have calculated the density function, using that I can find out what is the probability of finding the state between any two values. Not only that, there is another major advantage of finding the probability density function. See, what are we talking about? We are talking about the probability of finding the state at a particular value. Now, from that obviously the average should be extractable. Is that point clear? Should be extractable. That means, what is the average, what is the mean square? That information must be contained in the probability density function. So, once we have obtained the probability density function that contains the information about the average, the mean square and stuff like that. For example, what is the average? The average value or DC value would be, we will say x, and what is the probability of finding the state at a value of x, that is times p x. Okay. Then that will have to be integrated over the whole range. So, integrated from minus infinity to infinity x p x dx, okay. That will be the average. So, notice what I am saying. Now, I am allowing the x to vary over the whole range minus infinity to infinity, and at each point, at each value, what is the probability of finding? So, it is weighted by the probability. Naturally, if x has a larger probability of being very close to 0, then that particular value of x will be multiplied with a higher probability, while larger value of x will be multiplied with a lower probability. As a result, this integral will yield a value that is close to 0. That is intuitive, because you had the average close to 0. So, this is nothing but what we had said mu x. Similarly, can you say what will be the mean square value? X square, yes. So, mean square value we were denoting it by psi x, x because it is function of x, square is equal to integral minus infinity to infinity x square times p x. So, this is the advantage of finding the probability density function, that from there we can derive many informations. Once we have derived the probability density function, we can derive many information, and that is exactly why we were so keen on working out those Frobenius-Perron operators, trying to work out the averages, essentially try to work out the probability density function, so that these information which are of practical importance can be extracted out of it. Okay.
So, mu x square, why we take x square, not x minus mu x whole square?
What? I didn't get it.
So, can't we take x minus mu x whole square in the last expression?
Here?
Yes.
No. Here I am not talking about only the AC component. Here we are talking about the total power that will be dissipated if it went through a resistor of 1 ohm. If you take x minus mu x, essentially you are talking about the AC component. Mu x is the DC component, x is the actual the variable. If you subtract the DC component, you get only the AC component remaining. Its mean square is that gives you the power that is dissipated by the AC component. But in this case, you are interested in finding the total power that will be dissipated if this current went through. Probably this is common, right? This has been done in earlier classes, I guess. Only this is being used in this specific context. There is another thing that we are interested in, which also probably has been covered in your maths courses, that is how is the present state correlated with the history. It is given by the autocorrelation function. Have you come across that? Probably 80% of you have. So just recall what it was. The autocorrelation function is trying to correlate x at time t with x at time in the past or in the future. Okay. They would be the same. If I am standing here and I look into the past and try to find out, then I will write xt and xt minus tau. If I am talking about that state and how it is related to the state now, essentially we will take xt and xt plus tau, same thing really. That is why what we will get is actually even function. So we will talk about xt and how is the correlation quantified? Simply by the product. So xt times xt minus tau. Well, tau is the amount of gap that I am trying to explore. That means if the state is here now at this point, then how is it related to a state that is tau times in the past? So that is a tau. So we obtain the quantification by simply obtaining the product, and then this is specific to a specific tau. But then here I have talked about a specific xt. So there was a waveform at time t, it had a particular value. How is it related? But basically what I am asking how is the whole time series related to the history. So I will have to compute it over the whole time series, which means that this will have to be integrated over 0 to t. And it has to be averaged over. Okay. Yes. Also, we need to take a very large time series, ideally infinite size. So we have to take. So ultimately, what we have arrived at is some kind of a quantification of the state's dependence on history, and that is called the autocorrelation function, represented by r of x, and it will be function of tau, okay, function of the delay that I have taken. Is that clear? So, so this is the autocorrelation function. We are generally interested in finding it for chaotic time series also. Fine. So this is the autocorrelation function. We can easily imagine a few characteristics. The way I said that it will be the same if you take the tau positive or negative. Why? Because the way, say I am talking about tau is equal to 1 second. If the state, if I am asking the state now, how is it related to the state 1 second earlier, and if I talk about the situation how the state 1 second later is related to the state now, it is the same answer, because it is I am talking about 1 second. So essentially it is a even function. We can write it as r x minus tau is equal to r x. Okay. So it is a even function, that is it is, do you know what is even function? Yeah, that means if you imagine a mirror on the y axis, it is a mirror image in the other side. That is the definition of even function. If tau is 0, then what do you have? Yes, it yields psi x square, right? If tau is 0, you essentially get the same thing as psi x square. That means the you get back what you have already done. So, okay, one thing is sure, that the value at tau is equal to 0 will be larger than all other values, because it is very correlated with itself. The more you go in time, go away in time, it will be less correlated. It will be the maximally correlated with itself. So, the correlation function will have a peak at 0, tau is equal to 0. So, we can write Rx at 0 is greater than Rx at tau. We can say magnitude for all tau. Now, we have already arrived at the conclusion that Rx 0 is okay, and if Rx is if the tau is allowed to go to infinity, then what? No, wait, notice, try to argue it out. At the tau equal to 0, that means I am asking how what is the correlation between the state now and the state now. Then I get a large number, and that is the psi x, fine. So, if I ask what is the correlation between the state now and the state infinite time earlier, will we really get 0? No, we will not get 0. Suppose there is a DC value. Suppose there is a DC value, that means mu x is not 0. So, there is a DC value, on top of it some waveform is there. If you go to infinity, that correlation will go to 0, all right, but the DC value will remain. Is that point clear? That is why if you allow the tau to go to infinity, what you extract is essentially the DC value, or since there is a square of it, essentially you get the square of the DC value. So, you can write mu x is nothing but the square of Rx at infinity. So, we started with the premise of the DC value and the mean square value, and we learned how to obtain it from two different premises. One, the probability density function, and the autocorrelation function. Okay. There is another thing that would be interested in most cases, especially people working in electrical engineering are always interested in that, the frequency characteristics. That means how much power is available at different frequencies available in that waveform. If it is DC, the frequency is 0. If it is a sinusoid, the frequency has only one component. If it is a distorted but periodic waveform, we know that it has many components, many frequencies. If it is a chaotic waveform, it has all the frequencies. Okay. But nevertheless, what actually we are trying to obtain would be essentially the power contained between two frequencies, f and f plus delta f. So, you would imagine that we have designed some kind of a band pass filter that allows only this range of frequency to pass. If in the input side we put that time series, in the output side we have only that component that falls within this range, and we say obtain we are trying to obtain the power, so we obtain the mean square value. So, that is what we are up to. So, we will say the mean square value in the range f and f, not in the range, it will be function of f and delta f, that will be again integral of 0 to t, but what we will integrate? Now, we will integrate x square that falls in the range a square of t, and it will be also a function of f and delta f. It will be function of time, it will be function of the frequency and the frequency range. We have extracted that information and we integrate over time, averaged, and we take the limit. What have we? We have essentially the power that is contained in this frequency range. That is what we have obtained. Well, now the power spectrum, power density spectrum is nothing but this situation where the delta f is slowly reduced to 0, and you divide this by delta f and let delta f vanish. So, that is how we get the power density spectrum. Okay. So, the power density spectrum we will write it as g x, it will be function of f, it will be this term psi x square f and delta f divided by delta f, this term divided by delta f, while limit delta f tending to 0.
So, could you explain the term x square t comma f comma delta f?
Yeah, here we had the original signal x of t. Okay. We said that we imagine we have placed a band pass filter that allows only that component to pass which falls in this frequency range. Okay. So, we have essentially selected out of the whole signal, there are many frequency components, allow only that which falls in this particular frequency range to pass. So, we get x of time, but in the it is also function of f and delta f. We take the square of that, and then integrate over time. So, that is that yields the power density spectrum, PSD. You will find that these are nowadays automatically measured in some of the CROs, but obviously not through this route, it measures through a different route. I will come to that. So, this will always be a real valued function. Okay. This will always be a real valued function. The power density spectrum, we have got some kind of a for every frequency there would be a value of power, another frequency another value of power, another frequency another value of power. In case of again in case of a DC, it will be peaked at 0 frequency, nowhere else anything. In case of AC sinusoid waveform, it will be power concentrated at a single frequency. If it is distorted sinusoid, it will have many third harmonic, fifth harmonic, and so on and so forth. That means power concentrated at those. And in case of a chaotic waveform, it will be a continuous power spectrum. Okay. But this is the definition of power spectrum. We must understand that. But actually obtaining the power density spectrum is not done by this method, because you really do not construct a band pass filter and allow it to pass. This is a good way of visualizing what it is, but actually it is done through the Fourier transform. So, this comes through the root of the Fourier transform. Probably you all have done Fourier transform. I know that some of the students are more comfortable with Fourier series rather than Fourier transform. Is that right? No, Fourier transform is easier. Good. I have seen many students who at the time of the Viva Voce test says that I understand what is a Fourier series, but I do not understand what is a Fourier transform. You understand, right? If you do, let me give you a problem. Problem that I find very interesting. As you know, in the olden days, by the way, let me write down the Fourier transform so that we can refer to that. Okay, I'll come to that later. In the olden days, the view of the solar system that people had, do you know what it was? The Ptolemaic picture. It was that the Earth is at the center of the universe, the sun rotates, the moon rotates, and all the planets rotate around it. And do you know what is the problem of the rotation of the planets? I mean, if you go to any field in the evening and observe the motion of the planets, for example, Mars maybe, and how would you try to figure out its motion? You would simply take a graph paper like this, and on one day you will measure the positions of the stars, and then say also the position of the Mars. The next day you would go out, take it like this, and then the position of the stars will be the same. Relative positions of the stars will be the same, but the Mars's position will have moved a bit. That is why it is a planet, it is a wanderer. So, again make a mark where it is in the starry background. Next day again come and do that, next day again come and do that. Then you will be able to plot the trajectory as seen from Earth. Okay. And in fact, that was done more than 2000 years back. Aristarchus did it first, and he noted that it is a very, very peculiar waveform. It is like this, it goes and then turns back, and it goes forward and it turns back and it goes forward. So, it is like this. So, anybody trying to design a model of the solar system has to account for that. So, what Ptolemy did was, he proposed that the planets do not really go around in circles, but there are circles over circles. Okay. So, he said that inside there is the Earth where we are sitting, that is the center of the universe, and the planets are moving like this, but not only like this, but they are moving like this. So, for some time you will see them going backwards quite naturally, and then astronomers started pointing their trying to find out whether the actual motion satisfy that. They said they found that no, not really. And then the post-Ptolemaic people said that okay, not only one such epicycle, but there are more such epicycles. One big one, small one, even small one, and that way they tried to fit into the picture. And by the time it came to the time of Copernicus, Galileo, that picture become horribly complicated, because it turned out that they were starting to compound epicycles over epicycles, and it required a huge number. And then Copernicus said, okay, let us take a fresh look at it. Imagine that the sun is at the center, we are rotating, they are rotating like that. But there is a theorem that says that if you go on compounding an infinite number of epicycles, you will see exactly the thing that we see from here. They stopped because you really cannot do that. Can you explain this observation on the basis of the Fourier transform? Post Fourier, we know why what really went wrong. Before that, we didn't. Think. It's a good problem. Okay, what the Fourier transform is something like this. That means, let me state the problem properly. The actual motion of the planets can be properly explained by considering an infinite number of epicycles, If you are really compounding an infinite number of epicycles, you will see, you will be able to predict the exact motion of the planets. Still that picture is wrong. It is not that there are the earth is really at the center and it is just a picture, it is a representation, but that representation would work. Okay, think. So, if you have a signal x t the Fourier transform is given by multiplying it with a exponentially decaying quantity, which is, so exponentially decaying because you want it to be ultimately finite, the integral to be finite. It would be minus j 2 pi f t dt integrated over minus infinity to infinity. So, what you will ultimately obtain is x of f. This is capital X and this is small x, remember. When it is a function of time, we represent it with small quantities, and when it is the function of frequency, it is the capital. Okay, so, this is the Fourier transform. And of course, the inverse Fourier transform it can be obtained as x t from x f minus infinity to infinity. Now, I have to integrate over x over f. So, x f e to the power j 2 pi f t d f. So, that is the inverse. So, this is the f Fourier transform and this is inverse Fourier transform. What is the relationship between this and the power spectrum? Power spectrum is nothing but the square of the Fourier transform. So, that is the essential idea from which it is actually done by most of the modern storage oscilloscopes. So, the power spectrum okay. So, power spectrum is nothing but the square of this and what actually most fast Fourier transform machines do is to obtain a transform and then take the square of it, that is what is displayed. Probably you have seen those oscilloscopes which readily get the data and display the spectrum, it does it that this way. But remember, we are interested mainly in the power spectrum. Engineers are interested mainly in the power spectrum, not this quantity. For our purpose, it makes more sense to talk about the power spectrum. Now, since probably you know that for even functions, this can be simplified to a cosine term, right? You have heard of it. Now, is a chaotic waveform a even function? Well, in a statistical sense. In the statistical sense, you can say statistical sense means if there is a waveform, it is irregular waveform. So, you cannot really say whether it is even or odd, but statistically if you see the waveform and place a mirror and see the other side, you will not be able to distinguish them statistically. That is why statistically the cosine transform also works on chaotic signals. So, in that case you will write now it is half of it 0 to infinity x t then cosine okay. So, this is a simplification that is applicable only in case of even functions, and since chaotic waveforms are statistically even, that is why this works. We often obtain the Fourier transform by this method. Now, the question is, supposing we have obtained this, can we extract the quantities that we are talking about earlier? What quantities we are talking about earlier? The DC value. What is the DC value? Can we obtain it from the Fourier transform? Of course, it is the quantity around 0. So, how will you obtain it? Mu of x is that is integral from where to where? 0 minus to 0 plus of what? Wait a minute, let me see what we have obtained. Okay, this we had represented as g of f. So, I will write g of f here, g of f power spectrum df. Is this right? No, it is not right, because 0 minus to 0 plus, you have taken both the sides, but now it has to be ultimately g of f is square of what we wanted. So, you have to take a root of that. You need to take a root of that. So, essentially if you have as the power spectrum, you take the very small quantity between 0 minus and 0 plus, this height, and the power spectrum is, you have already taken a square. So, you have to take a half. So, if you know the power spectrum, from there the average can be, or DC value can be extracted. What about the mean square value? Can we extract the mean square value from here? Well, mean square is nothing but the total power contained in the signal. Now, you have decomposed it into the frequency components, and therefore, you have to take integrate over the whole frequency. What you get ultimately, that is nothing but the intuitively speaking, that is nothing but the mean square. So, you have to take the area under this curve. That will yield the mean square. So, sorry, psi x square, here we are talking about psi x square. Again, we will do it over half, because the other half is not necessary. G x f df. Here we are integrating in the from the left side of 0 to the right side of 0. Here we are integrating over the whole range. We are through. Okay. So, two things we have extracted. After that, where did we go? Autocorrelation. Fine. So, the next question is, how is the power spectrum related to the autocorrelation function? There is a very important implication, and many of the modern gadgets depends on this implication. They actually obtain the autocorrelation function and then obtain the power spectrum from there. Because the autocorrelation is easy to obtain. In order to do that, let us proceed this way. Let us first take the inverse Fourier transform of the of this minus infinity to infinity. We will take the power spectrum, which is x f square. We start from there. We take the inverse Fourier transform, which means times e to the power twice pi f t df. Oh. Fine. So, we started from this quantity here, and we are taking its inverse Fourier transform. Let us see what it yields. Now, this can be written as minus infinity to infinity. Here it is, I can write x f times x f e to the power j twice pi f t dt. Now, let us invoke the convolution law. Probably you all know the convolution law, one of the elementary things that one does in signal processing. So, what is the convolution law? Supposing there are two signals x t and y t, then x t convolution, it is denoted by a star, x t convolution y t is integral minus infinity to infinity x t y t minus tau d t, okay, d tau. Oh, x tau y t minus tau d, okay, yes, fine. I mean, you might also reverse the notation like x t y t minus tau d t, that's the same thing. Okay, so this is the definition of the convolution, and we also know the convolution is the same as product of the Fourier transforms. We have learned that. I am not proving that, we have learned. That means, if x t has the Fourier transform x of f and y of t has the Fourier transform y of f, then x t convolution y of t has the Fourier transform x f times, that is the convolution law. Now, imagine that I make x and y the same signals.
Whole square is not equal to xf into xf in the first equation.
Why?
xf into xf conjugate equal to mod xf square x star magnitude of
Yes, but here we are talking about the, wait, are these, do we need to take the conjugate? These are real signals, I think. Huh? No, will these be?
if it is a complex function, then it's
Wait, I'll come back to this later, because if it is real signal, it is okay. If it's complex, then you have to take star. Yes, I'll come to that later. So, if you take x and y the same signals, then what does it yield? It means minus infinity to infinity. I am starting with x f square power spectrum times e to the power j twice pi f t d f. That is where we started. We said we are dividing these two. Now, if these are the same signals, then obviously this yields x t convolution x t, and x t convolution x t means integral minus infinity to infinity x t x t minus tau, right, and this quantity is so, which means if you take the power spectrum and take the inverse Fourier transform, you get the autocorrelation function, and if you naturally if you take the autocorrelation and if you take the Fourier transform, you get the power spectrum. Okay. So, the power spectrum and the autocorrelation function are nothing but the Fourier transform pair. Okay, that is the important result that is often used in practical instrumentation. Okay, we will stop here and continue in the next class with the same idea.